time for a discussion.
Pocket.
All right, we had such a great slate of talks today. It was hard to pick some discussion questions, but we came up with a few, and hopefully we'll have a good discussion today. So go ahead.
Yeah. All right, so we basically have 5 questions. Let me make it full screen. Let me know if it's too small. We can zoom in. So the first one is galaxy environment is clearly correlated with galaxy properties. What is the most relevant parameterization of environment? Is it large-scale density or cosmic web? Filament versus node? Should we use instantaneous environmental proxy, or as Frank and Claude Andre the other day suggested, some average or history of environmental parameters? Does environment mean centrals versus satellite, or simply cluster versus field, or just a halo mass or group class mass? Yes.
This was inspired by a great talk today we heard about properties of galaxies as a function of distance from the node versus the filament. Anyone have any opinions about that? Near?
Near?
I would venture to say that your position in the cosmic web is important. I know Joel might not agree with me, but I mean, for one thing, the kinematics of gas in different regions of the cosmic web are very different. There's been lots of work by Sandrine Codis, Clotilde Legel, as well as our collaboration currently in preparation with Avishai and Frank and some others, showing that there are lots of really strong vortical motions in filaments. It's been suggested that galaxies that kind of lie at the outskirts of these filaments fail to accrete additional gas and begin to quench just because of all the vorticity in the filaments. It's also been shown in a paper from 2013 by Benitez Vamble, as well as a recent paper by our collaboration led by Imad Pasha, that large-scale structure shocks associated with cosmic web environment can quench low-mass galaxies in very similar ways to environmental quenching that we see in clusters, but depending on where you are in the cosmic web and whether that you can be shielded from such effects or not. So, I mean, and I'm not even talking about the the different tidal fields in different cosmic web environments, which are clearly important. But I would certainly agree that this is a topic that needs to be studied more, and the sense that I've been getting over the last few years is that more and more people are studying it, so it should be fun.
Well, I was just wondering if anybody, aside from Farhan and his advisor, have been looking at the contribution of entropy in these different kinds of environments.
Any opinions on that?
Yeah, regarding the halo mass, I think it's not the most important thing is not the cluster mass itself, but it's a related mass is hierarchical in the nearby field. If it can, for example, in the node, if it's a massive halo, it can dominate the local potential, and that will be very different for a satellite. I think the relative mass will be more important than the simple, the absolute mass.
Any other opinions?
Because the angular momentum vector seems to be different for small galaxies that's within the, let's say, called the ribbon of a filament versus those that are bigger, which have a sort of a different angle with respect to the filament, I expect that maybe the distribution of the mergers will be quite different if you look at them maybe through simulations. And perhaps a suggestion for the theorists is to see if you could see that, yes, statistically, small galaxies that are within filaments, for example, have a different average impact parameter relative to their size compared to those which are larger. Similarly, small ones that are further away may have something different. And there is something that maybe the observers in hand can then get a handle to test them. I mean, it's fine to talk about all kinds of possibilities, but if you can relate them to the observers' measurable quantities, that might be useful. So the key point is I'm thinking that the merger properties in terms of impact, relative angles of the angular momentum vector might be an interesting addition to the pool that you've listed there.
Yeah.
I just want to bring about one interesting paper, like kind of related to this idea that. So there was a paper from the 300 simulation that says that the galaxies in the filament might be more quenched than the galaxy outside the filament, but the galaxy in the cluster in filaments is less quenched than the galaxy in the other directions in the cluster. Kind of opposite effects of what you might see in the large scale density environment. So yeah, so I just want to point that out real quick.
Okay.
All right.
Looks like we don't have a decisive answer. I guess the most relevant environmental parameter must depend on which aspect of the galaxy you look at, right? Like David mentioned, if it's mergers or angular momentum, then yeah, definitely the filaments matters versus node. All right, shall we move on to the next? Also motivated by a very nice talk by Oscar and Dusan this morning. Has the Milky Way history been solved, the constraint? Can we constrain the Milky Way assembly using the halo or thick disk star metallicities? Can we use the disk sizes? Is this sensitive to the properties of the last major merger? And which aspect of the last major merger is more important? Is it the mass ratio as shown in this figure? Or is it just a polar orbit that gives rise to this bimodality? And how generalizable is the Milky Way's history to other galaxies? Any opinions? I personally was very interested by this idea, right? So different merger mass ratios lead to differences, but also this in this particular simulation, it was a quite polar merger, right? Joe.
Well, I'll make a point that we made in a paper by GOH, me, and others several years ago. And there's a related paper by Andrei Krausov, with the first author being one of his students. And the point was that the local environment of the Milky Way is quite unusual, the Milky Way and Andromeda. What we said was we looked for sheets, the sheet in the cosmic web, which is the border of a void, and the Milky Way and Andromeda are at the center of a fairly small sheet. It has a radius of about 4 megaparsecs And all around it, there are about 8 or 10 quite massive galaxies, all at just about the same, just as what you'd expect for a filament. Filaments surround sheets. Now, that's not unusual to be in a sheet. What's unusual is to have two rather massive galaxies in the middle of such a small sheet. We found all the sheets in the Bolshoi-Planck simulation, there are about 1,000 that size, and there were only like 4 or 8, depending on what our criteria were, to be such massive galaxies in such a small sheet. Kravtsev and friend argued that we had imposed too many special conditions, but from their analysis, they also concluded that the local environment is extremely unusual. Most galaxies lie in filaments, especially most fairly massive galaxies, or nodes. So that's an interesting thing to take into account. Just to give an example, it's generally found that the angular momenta of dark matter halos in sheets, the angular momenta tend to lie in the plane of the sheet. The Milky Way's angular momentum lies exactly in the plane of the sheet. The disk of the Milky Way is almost exactly perpendicular to the sheet. Incidentally, the ring of satellites around the Milky Way is in the sheet, which of course is not surprising if that's where they came from. Anyway, so at least one aspect of the Milky Way and Andromeda are quite unusual and are, as far as I know, never mimicked in simulations.
Fascinating, yeah.
Thanks. A somewhat naive question. To the extent, and I don't even really know the answer, but to the extent that we can constrain the Milky Way assembly history using halo or thick disk stars, and to the extent that's been done, how well does that agree with constraints on the Milky Way assembly history that people have obtained using globular clusters, chemical tagging, stellar streams, things of that sort? Maybe somebody knows.
Does somebody know the answer to that? Okay, so then I'll get back to you.
Since there's been pretty broad agreement across several lines of evidence, globular cluster populations, halo stars, and morphological and elemental abundance distributions in the disk of when at least the 2 or 3 most major merger events occurred. So I have not seen personally any strong tensions. I think it's, on the first question there, has the Milky Way assembly history been solved? I think maybe to first order, we have a pretty good handle of that. There's claims that now we can basically account for about 95% of the mass of the stellar halo through, the 7 or so or 8 merger remnants that we can identify through kinematics and abundances. On the other hand, I think we'd like to think that with the Milky Way, we can go to second or third or even fourth order effects on the assembly. This is the one galaxy for which we should be able to get a very deep understanding of how it forms. So I think, at this point, perhaps the first order picture is coming together and, future work is higher order. I wanted to make just a comment relating to what Joel commented on about, how generalizable the Milky Way's history is to other galaxies. Just something we found that, with the small number of statistics we have on our Zooms that we were talking a little bit over lunch, is that I think there is evidence that the Milky Way is probably an unusually early settling disk. And within FIRE, at least, we have 2 suites of both individual Milky Way systems and then those in local group environments. And we've looked a lot at the differences between how much does it matter that you're simulating a local group versus individual Milky Ways. And for things like the satellite populations, we've basically found no meaningful differences, I'd say. The one thing that has stood out, but I think is still tentative, is it's pretty clear that the galaxies, the Milky Way and M31-like galaxies forming in our local groups form earlier, and they have more extended disks. So, and those are probably related statements, but I'm not sure we've unpacked that in great detail. So I think, beyond the broader environment, just the local group nature that the Milky Way finds itself in probably is an important factor to consider when we think about the history of the disk and how early it may have formed.
Yeah, so I think I was going to say something that I think builds on what Andrew just said, but on this point about generalizability, I think something that many of us are thinking about, but increasingly needs attention is, as our understanding of the Milky Way's assembly history continues to get better, and the data gets better for the Milky Way and Andromeda and local group galaxies, I think we're increasingly confronting this problem that Oscar alluded to in his talk, and we were joking about at lunch. None of our simulations is ever going to be the Milky Way, even if we had the perfect physics, right? We're not going to exactly match the Milky Way's weather today. And I think for a lot of quantities, there's quantities where we know how to handle this. Satellite luminosity functions, simple one-dimensional distribution functions, we know how to compare and say, is the posteriori probability of my few simulations consistent with drawing the Milky Way? But there's a lot of these higher dimensional things, like the halo substructure is a relatively simple but still more complicated example that even that we haven't really figured out a proper posteriori way of quantifying, is my simulation consistent? Usually what we do is we say, there's a qualitative thing in my simulation that looks roughly like the Milky Way, I'm happy, right? Or one of my 5 simulations, right? And I think, we really need to, I think that's the crux of this generalizability statement is, how do we probabilistically model those kinds of things? And I think we're struggling with that with a lot of things.
David.
Another aspect of the Milky Way that's rather unusual is this extremely small supermassive black hole. And I believe that it's an outlier. And secondly, if it does reflect the history of perhaps a merger process that happened a long time ago, it may indicate that that particular merger process had perhaps a slightly unusual impact parameter or different angular momentum vector differences or something. But I can tell you that Milky Way is not common in that regard. You look at other galaxies of similar total mass, certainly it's odd, but it does have a rather small bulge. And given that Andromeda is similar mass to the Milky Way, it's in some sort of group environment, et cetera, it's a factor of almost 100, I think, in difference of supermassive black hole. So maybe the theorists can come up with a way to use that as another constraint on which ones are more likely to be comparable to Milky Way or not in terms of accretion history, assuming that the bulge does reflect that aspect in some way.
Yeah. There are also other aspects of the Milky Way that are special, right? Like the satellite quenched fraction.
Why don't you mention that? Compared to Saga, as far as I know, Saga's never found another one that's as quenched as the Milky Way.
Yeah. Yeah.
So just something that I think people generally know. So Saga aims to find 100 Milky Way analogs, and they're pretty close to that. They've published 2 places along the way. But as far as I know, they've never found another set of galaxies that have satellites as close in as the Milky Way dwarf-spheroidals that are as quenched. In general, their satellites tend to be blue. Although they also did find a general trend that the closer the satellites are to the central galaxy, the lower the star formation rate. But that's another way that the Milky Way and Andromeda are unusual, and maybe related to the other ways.
Yeah.
Right.
Cool. Should we move on?
Unless anyone else has a burning comment? Okay, well, we
Okay.
went from large-scale structure to the Milky Way, and now we'll go down to satellite size.
Small scales. So is core stalling relevant for galaxy scale evolution? Or is it just relevant only for compact stuff, black holes, globulars? Is it relevant for like compact satellites that Avishai and others mentioned the other day?
Inspired, of course, by Frank's talk today.
Yeah.
Yeah.
I'll just mention one other way it might be relevant that Fengju, you and I have talked about a little bit is, building nuclear star clusters or proto-bulges, right? There's a, I think this is a nice example of, there's this and other phenomena can sort of lock you into a chord, puffy density profile, and it's sort of an attractor solution where once you get into that, it can be very hard for the galaxies to sort of break out in the simulations from that solution. And as a result, this may be closely related to the things we heard about the size the distribution of sizes problem and the lack of compact dwarfs or compact structures in dwarfs in some of the simulations. So
Yeah.
that's one more example.
Cool. Yeah. That's actually exactly the next topic. The structural diversity. Yeah. Cool.
So we heard from Avishai a couple days ago that we need compact satellites in order to form the core, but we need the core in order to see core stalling. So as Frank showed today. So which came first, and how do we reconcile those that particular conundrum? Any opinions?
David.
So, first of all, thanks so much, Frank, for a wonderful lecture on it, and made me wonder whether I don't know, this is a question to the audience, do we currently understand the distribution of the core cusp distribution of even bigger galaxies? People like Sandy, my colleague, has studied this, decades ago, and I'm just wondering whether is that a puzzle, or is that well understood, the distribution of the core cusp number as a function of mass and maybe ellipticity of the galaxies, et cetera, et cetera. Is that something known? I'm really asking as an ignorant person here.
I think no, we don't. I mean, we think we know there's one place where we see cores in stellar distribution, right? It's the most massive ellipticals, and there the idea was the core was by scouring of black holes that then merged. But if you take this core stalling picture, that once I have created a black hole that has scoured that core and now sits in that core, little perturbations should be able to get it wandering, and if dynamical buoyancy operates, it should push it out. I think that's inconsistent. Whenever we look at these giant ellipticals, we pretty much see that the black hole, well, I think we see that the black hole sits at the center. In dwarf ellipticals, it's not a case where we postulate the presence of cores, both in the dark matter and unsubstantial contribution of stars. There, we often see nuclear star clusters in dwarf spheroidals. Initially, I thought, okay, that's going to be a killer to this idea of core stalling. A little bit more closer examination, and again, I would love to hear from observers, it actually appears to me that the nuclear star clusters quite often are significantly offset from the center, from the photometric center. And the same thing for the AGNs that were recently discovered in these dwarf galaxies by people like Reines and collaborators. They seem to always have an offset. So maybe that's a hint that there's something like this going on. But then why don't we see it in the massive ellipticals? I don't know.
Good news for young folks, lots of puzzles out there.
Just a quick comment following up on what Frank said. As far as I know, no one has ever found a massive elliptical galaxy, in fact, a massive spiral galaxy for that matter, without a massive black hole at its center. Isn't that a problem? In black hole mergers that are not the same mass and that are opposite oriented spins, you expect kicks of up to 1,500 or 2,000 kilometers per second, which should be enough to remove the black hole entirely from the system, or at any rate, make it go far from the center. We have never seen that. Does that mean that these mergers are actually quite rare? Maybe the last parsec problem isn't really solved in nature? Or is there something else that we're missing?
I think related to that, I mean, the work that Michael Trammell has been doing, where they actually model these things in simulations. They predict a vast population of black holes that are swarming around in space, and you know, the work that Colin showed us, there should be, you advertise that paper without going into it. I would love to see what your predictions are for how many off-centered AGN should be floating around and we should detect them as AGNs. And how, you showed the X-ray luminosity function. How many of those X-ray sources are not at the centers of their own galaxies, and is it consistent with current observational constraints? And I think it all relates to the wandering of the black holes.
Yeah, some great questions here. Definitely a lot of problems to be worked on.
Yeah.
We have, okay.
Joshua.
I have a question for Frank. When you consider the core stalling, what will be different if you put the perturber as a point mass or a unbody system as the perturber, like a global cluster or satellite galaxies? Will it be either lead to different final results?
Our calculation was done assuming some plomosphere with a certain size. I don't think the size is going to matter that much. I think that's a maybe second, third order effect.
We are also doing simulations.
That's what the simulations we create around it.
I asked this because I thought when we consider the mergers, the black hole initially was not next.
Maybe.
It was embedded in a satellite channel. If that makes a difference, maybe.
Okay, maybe move on to the next. Yeah.
Okay.
So there was this argument about 6 or 8 years ago by Blagovich et al. That gas will tend to align the spins of merging black holes, merging supermassive black holes. And if the spins are aligned, you do not get such a strong kick, but you'll still get kicks of a few hundred kilometers per second, which still makes it puzzling why they're not wandering and they're always found right at the center. So I think the whole thing is really a deep mystery that mostly isn't discussed in the literature as far as I can tell, except maybe the Tremel papers.
There was one more here?
I was just
No.
going to mention very briefly on that. There's also a series of papers by Laura Blecka on modeling kicks in the hundreds of kilometers a second regime and things like the ring down time for the resettling sector. So there might be some partial stuff towards that end of the paper.
Wow, great discussion we're having. Okay, so we did have one more.
Yeah.
I mean, or actually we had two more, but we have a few more minutes, so we'll just do one more question. This one might inspire a little bit more discussion here.
Yeah. Structural diversity issue of dwarfs.
Yes. you go.
Okay.
Right, so where can we look for solutions to the structural diversity problem in dwarfs? So we have a list of here of possible solutions. Feedback.
Environment, maybe alternative models for dark matter.
Yeah.
Motivated
Weak
by
lensing, POP3 stars. we
yeah,
put in there
POP3
too, yeah.
stars. Some dwarf version of compaction. We learned from Yifei Luo's talk that the Marian survey can potentially help to observationally constrain some of the morphological diversity. Yeah. But on the theory side, what's missing? Yeah. The problem is manifested in simply galaxy size versus stellar mass, or in the inner dark matter density slope. The right-hand plot is from Nicole Relatoris a few years ago. Kinematics inferred inner slopes and compared with for the fire simulations. Look at this.
Two comments. One is, I don't know the answer, but we've talked about, we've tried and other people have tried a number of alternative dark matter models, and it's not as easy as you might think, even when you free the dark matter model. As was alluded to earlier, you can shift the mean, but it's very hard to create that spread in the population.
Yeah.
I do think, especially for the slopes, less so for effective radii, but especially for the slopes. This is getting to the this problem is, as we move to each level of increasing subtlety of modeling, rotation curves and things like that, I think we really need to do apples to apples comparisons.
Right.
Spark is plotted here. Spark has a strange selection function, and the rotation curve is really what a tilted ring model thinks from an H1 data cube is the rotation curve, and all the theory plots are, GM enclosed over R, right? So
Sure.
I think for this level of detail that we've reached, we really need to be more careful about that.
Agreed, yeah.
I just realized actually that we are slightly over time. So is there one more burning comment that anyone wants to make about any of this? Oh, okay.
Keep in mind that us observers have found streams that are a result of mergers in which there is evidence that dwarfs are formed along those streams. I don't know whether they're gravitationally bound, but nobody's talked about them here. I'm just noting that there are perhaps other mechanisms for forming dwarfs than what's been discussed in this particular workshop. So there's more variety to the universe than whatever the poetic phrase is we can imagine.
Okay, one last one from Frank, and then we can
Call
we
it
can
a
all
day.
be dismissed.
It's more a question to maybe someone knows the answer. In terms of the diversity issue, when you look at the dwarfs, those scales, what is known observationally and in simulations about bar fractions of those systems? Because rotation curves and bars don't go hand in hand. It's always an annoying thing. So do the simulators reproduce observed bar fractions in those systems? Does anyone know? Do we know what a bar fraction is in those systems? I don't.
I don't.
We know observationally?
I think we don't know.
I think so, yeah. I mean, for example, the one case is always shown in the diversity plot with one of these things with a rotation curve that's like a straight line. I put my money on a bar there.
Galaxies do. The majority of spirals of something like that are bars.
Milky Way mass, but this is at the SMC kind of scale there. Yeah, but at the Milky Way size, we don't have a diversity problem.
Yeah.
All right.
All right.
Thanks, everyone,
Thank
for
you,
a great
everybody.
discussion. Let's give a hand to all the speakers again.